Good afternoon. Resuming with what we have in the test 3 review, we have just going back to the quadratic functions, and we have with the first question, okay, we have a given function f of x is equal to negative 2x squared plus 16x minus 36, and we're looking at answering the following three questions. And we're looking at whether the function has a minimum or maximum value, and also where that minimum and maximum value will occur, as well as determining just what that minimum or maximum value will be. And now, again, there are two ways of expressing quadratic function that are commonly used. One is the standard form, and the other is the vertex form, okay, which we have the general layout of f of x is equal to a times the square of x minus h, followed by the addition of k. And if I were to take this particular function and rewrite in terms of the vertex form, okay, so going from this standard form to the vertex form, okay, I can begin by separating the variable terms from minus 36, the constant value. And so we're going to have, and setting things up, okay, so we got f of x is equal to, and so I'm quantifying, okay, we have negative 2x squared plus 16x, followed by the subtraction of 36, and creating the pathway to ultimately factoring by grouping. Okay, now for what I have in the parentheses, if you did this beforehand, that is perfectly fine. I want the first term in the parentheses to be x squared without any coefficient other than 1 in front of it. And we have negative 2 in this particular layout. And if I factor out the leading coefficient, negative 2, okay, so I have negative 2 times the quantity. Okay, so I have x squared. And negative 2 into 16x is going to be negative 8x. And we have followed by the subtraction of 36. And we have entering the stage, okay, of completing the square. Okay, all right, and you can complete the square if you have the first term to be like just with the coefficient 1. In this case, you have 1x squared, and following through with the completion of the square process, okay, I can look at the number that is next to the first order variable. In this case, we have the number to be negative 8, and for the completion of the square, again, I'm going to take half of that number and then square. So here we have half of negative 8 is going to be negative 4. And we're going to have the square of negative 4 to end up at 16. And we have with this value, okay, so I'm going to add 16 inside the parentheses. Okay, so we have going to the next step. Okay, so we got f of x is equal to negative 2 times the quantity. Okay, and we have a x squared minus 8x, okay, and we have plus 16 and we have minus 36. But now there's a bit of an imbalance that is going to be created. Now as I'm adding 16 inside the parentheses, what I'm doing overall at the front, okay, is that as I'm adding 16 to the parentheses, I'm actually in the whole package, I'm actually adding negative 2 times 16. In other words, I'm doing the equivalent of subtracting 32 at the front, and I want to offset this created deficit by adding 32 at the end. Okay. And so we're going to have for f of x, okay, so we have negative 2 times the quantity of x squared minus 8x plus 16, and then we have negative 36 plus 32. Okay, that is going to be a negative 4. And you can always sort of go back and check. So I got negative 2 over x squared. Negative 2 times negative 8x is a positive 16x. Negative 2 times 16 is going to be negative 32. And negative 32 minus 4 is minus 36. And we are very close to the vertex form of this function. Okay, so we got negative 2, and with the square trinomial that we have at x squared minus 8x plus 16. Okay, so for this trinomial, now x squared is going to be the square of x, and in terms of how it got to the formation of the 16 after negative 8x, okay, remember, in terms of how we got to 16 in the first place, this originated from squaring out half the coefficient of the middle term. And in this case, it had minus 4, and again, that is going to reappear. Okay. So this is going to be the vertex form, and looking at what we have in terms of identifying all the items like the minimum or maximum, as well as where they occur and just what the corresponding value will be. Okay, so again, this is what we have for the general layout. And again, just kind of mapping with the vertex form. Okay, and so for the correspondence, okay, so we got, in the case of A, okay, so A is at negative 2. And with A as a negative value, okay, this signals that the graph is going to open down from the vertex. So that means that the vertex is going to be the high point. And since the vertex is going to be the high point, that is going to be the location of the maximum. So you got A at negative 2. Now for the other items of significance. Okay, so you have x minus h represented by x minus 4. Okay. So if you were to envision like x minus h equal to 0, okay, that is going to be represented by x minus 4. Okay, and so we have the x is equal to 4, and so this means that, okay, so our x and h value will be one and the same. Whereupon we have that x is equal to h is equal to 4. And for what we have in the case of the k value, alright, so we have that k is equal to negative 4. And so for what we have in the case of the vertex, okay, so you have like in the conventional xy coordinate system, again, x comes before y. And from the vertex equation, okay, your x is represented by h in the general format, and y is represented by k. And for what we have numerically, okay, so you have your h value at 4, and for the y coordinate, which you have to be at k, right, that is going to be at negative 4. Right, and so looking at what we have, referencing what we have in the first problem. Okay, and in terms of whether the function has a minimum or maximum value, again, the graph is going to open downward, so the vertex is going to be the high point, and that is going to be the location of the maximum. And second question, okay, we have where does the maximum value occur? And again, if you notice you got your x coordinates, it's asking for what x coordinate is the maximum value going to occur, and that is going to be your h value, which is going to be 4. Okay, so it's kind of like your h value is equal to x is equal to 4. And again, the vertex is located at 4, -4. And so for the function's maximum value in this particular case, that's going to be your k value. And that is going to end up at -4. And just looking at what we have regarding this quadratic function. And so let me kind of change the view a little bit on this. Okay, so again we have with the details. Okay, so again we went from the standard form to the vertex form, and again the vertex is a maximum, and the location of the vertex again we have at 4, -4. And just looking at what we have envisioning, okay, what we have for the graph of this particular quadratic function, and for this one, okay, we're going to have so you got 4, -4 for the vertex, and again you have the graph of this particular function. Again, so you have 4, -4. That is going to be, in this case, the maximum, and it occurs at x is equal to 4, and the maximum value, or the y coordinate, or k value, that's going to be at -4, and everything else in the graph, okay, is going to be beneath that point. All right, now for what we have in the case of the second function, now we have in terms of g of x, and we have that g of x is equal to 3x squared plus 30x plus 77. So we have another standard form that is presented. And for what we have in the case of this function, kind of like what we did with f of x for number 1, okay, we're going to convert what we have in terms of the vertex form. Okay, and you can factor out 3 beforehand, and I'll just use the gradual separation. Okay, so we got 3x squared plus 30x, okay, in the variable terms. Again, we have followed by 77, and again, to make the quantified expression, okay, to have the first inside term at x squared, so I can just factor out the coefficient 3. So we have 3 times the quantity of x squared plus 10x, and it's going to have followed by the addition of 77. Okay, so I have things set up whereupon I can complete the square. Right, so in the parentheses, first term is x squared, and we have with the first order x term, okay, we got the coefficient at 10, so we'll add a constant after 10x, and that is going to be from taking half the coefficient and then squaring. Okay, so we got 10 as the coefficient. Okay, and so we have half of 10 is going to be 5, and we'll have that 5 squared is equal to 25. And looking at taking what we have now, so we have with the modified presentation of g of x. Okay, so just so we got g of x. Okay, so that is going to be 3x times the quantity of x squared plus 10x. You have plus 25. Okay, and again, what I'm doing inside the parentheses is going to have an entirely different projection in terms of the overall picture, because I'm adding not just 25, but since I have this 3 out at the front, we will have overall, we will have the addition of 75 So that means that to offset the surplus, I'm going to have to take away 75 at the end. Okay, and so looking at what we have for now, so I've got g of x is equal to 3 times the quantity, and we have of x squared plus 10x plus 25, and we have 77 minus 75 is going to be at 2. Okay, and I can always double check, so distributing 3 over the trinomial, so I have 3x squared plus 30x, 3 times 25 is 75. If I add 2, I come back to 77. And now I have things squared away where I can provide the vertex form of this function. Okay, so again, just for the makeup here, so we have like the a value at 3, the k value at 2, and for that, which will represent x minus h, okay, I'm looking at from x squared, and we have the square of x, and now for the term that closes out the formation of the square of the binomial, okay, again, we initiated the completion of the square process, and to get to the addition of 25, I squared out positive 5, and whatever value I square out in the completion of the square, that is going to reappear in the vertex form. In this case, we're going to have a positive 5, so I have 3 times the square of x plus 5 followed by the addition of 2. Okay, and so just for the general layout, okay, so you have g of x, okay, which is a functional notation for what we say is y. And looking at how the terms are going to meet up, okay, between the general layout and what I have for the vertex form that defines this particular g of x. All right, so we got for the a value, okay, so you have the a is equal to 3, okay, and since 3 is positive, okay, so the graph opens up from the vertex. So if it's opening up from the vertex, up to the left, up to the right, that means that the vertex would be the bottom location, and so this would be the location of the minimum. And looking at what we have for the h and the k values, okay, so we have in projecting case, so we have x minus h represented by x plus 5, okay, so we have x is equal to negative 5, okay, so we have that x is equal to h is equal to negative 5, and again, just for the k value, k value is going to be at positive 2, and so we have for the vertex, okay, so your x and y coordinates will be the same as your h and k values. And for the ordered pair, okay, so you have negative 5 for the first coordinate, and 2 for the second. Okay, so we got a vertex at -5, 2. Okay, so just kind of restating here. So you got the vertex at -5, 2. Okay, and again, the graph opened up from the vertex. And we said that the vertex is the location of the minimum. And if you notice, we have with the next questions, okay, they have a reverse order of what was present in item 1. Okay, this time we have what is the function's minimum or maximum value? Okay, that was the last question from problem 1, but now it is the next question in problem 2. So for the function's minimum or maximum value, in this case the minimum, okay, this can be your k value. So the minimum value is going to be at 2, and in the case of where the minimum is going to occur, that's going to be your x coordinate or h value. In this case, that is going to be at -5. Okay. And looking at just the visual display for that particular function, so you got your graph of g of x equal to 3x squared plus 30x plus 77. And the vertex, again, we have an x equal to -5. And again, the minimum value or the y coordinate is going to be at 2. And everything else on the graph is going to be above. All right. Now, in looking at what we have with the next set of items, okay, and see, we looked at 3 through 5 the other day. And now for number 6, okay, we have looking at the following items here, and this is a multi-part problem, and we have centered around, okay, the function that we have for f of x, and we have items like the end behavior as well as the zeros and their multiplicities, and also the y-intercept, okay, and just taking what we have for 6. Okay, so again, we have f of x, and we've got like the negative of the square of x plus 1, and we have times the quantity of x minus 1, and I'm going to rewrite this. Okay, so just for what we have, just for visual purposes, just for the end behavior, you're looking at the highest degree term that would be formed. Okay, and for the highest degree term, okay, since we're stressing sign values in the mix, okay, so we're looking at applying all coefficients. Okay, so in the makeup here, okay, so we're looking at for the highest degree term, so I'm looking at involving -1, and for the square of x plus 1, I'm taking the higher order term within the parentheses and just projecting to the corresponding power. Again, x minus 1, that is just a first order, and the higher order term from that variable factor, again, is going to be at x. So just looking at the portions here, so we got -1 from the front. Then we have with the square of x plus 1. So x is the higher order term in that factor, and again, that's going to be to the second. And for x minus 1, x is the higher degree term. Again, we have to the first. And just carrying out what we have here. So got -1 at the front, x to the second. Okay, so we have x squared and x to the first, well, that's just going to be x. Right. So your product is going to be negative x cubed. And I'm just going to stress the coefficient, so this would be like negative 1x cubed. Okay, so the coefficient of the highest order term, okay, we have it negative 1. And for the degree of the function, that's going to be the power to which x is raised from the highest degree term. So you're going to have that n is equal to 3. And 3 is an odd number. Okay, so you have a combination here. Say if you have a negative leading coefficient and the degree is odd, that combination is going to signal that for the end behavior, remember, whenever the power is odd, it's going to be up one way and down the other. And whenever the coefficient is negative, in this particular case, you're going to have the motion to be, like rising to the left or up to the left. And also we have to the right, we have moving downward. So up to the left and down to the right. Let's see if I can fit this in. Yes, okay, so the end behavior you have up to the left and down to the right. And now for the zeros, and where the graph is going to cross as well as touch the x-axis. Okay, so we're looking at, again, placing priority on the zeros and their multiplicities. All right. So for what we have in this next part, okay, so for the next part, okay, so you have the variable factors. You have that x plus 1 and x minus 1. So we can go ahead and state that for the zeros of f of x, let me do this one other thing here. Okay, so you're going to have x plus 1 is going to be raised to the second power, and we have for x minus 1, well, that's just raised to the first. Okay, so for the zeros of f of x, so we have with x plus 1, we have the x is equal to negative 1, and with x minus 1, if that's set to 0, okay, we have the x is equal to 1. And regarding the multiplicity of each zero, okay, so negative 1 stems from x plus 1 to the second, and 1 stems from x minus 1, which is of first degree. And in terms of whether the graph is going to cross or touch the x-axis, okay. Alright, so negative 1 has a multiplicity of 2, and if the multiplicity is even, then the graph is just going to touch the x-axis. So it's going to touch at x equal to -1. And in the case of x equal to 1, the multiplicity value of that 0 is going to be 1, which is odd. And for zeros of odd multiplicity value, the graph is going to cross. Okay, so you have to cross at x equals 1. Okay. All right. And so for what we have now, okay, so the zeros where the graph crosses the x-axis, that's going to be at 1. And where the graph touches but does not cross the x-axis, that's going to be at -1. And in looking at finding out the y-intercept of this function, okay, so we've got our function laid out, and for the y-intercept, we can get to this pretty quickly. Okay, so we have for the y-intercept, so we're looking at y is equal to f of 0, and we have like the negative of the square of 0 plus 1, so I'm just filling in 0 for x. And just moving this on down. Okay, so got the negative sign, you have -1. And 0 plus 1 is 1. I'm going to square that out. 0 minus 1 is -1. So you got -1. Square of 1 is 1. And so just multiplying together, okay, you have the outcome to come out to 1. So your y-intercept is going to be at y is equal to 1, or as an ordered pair, you'll be looking at 0, 1, 0 for x and 1 for y. Okay, and in terms of the activity throughout, okay, and looking at the graph, okay, so for the y-intercept of the graph, okay, that is going to be at y is equal to 1. And looking at what we have in terms of the graph itself, okay, and okay, it says for this one, okay, so we have in plotting points, okay, so just key locations. Now we got the y-intercept, okay, so you have at 0, 1, and for the x-intercepts, okay, you got your 0, so you have x equal to -1, x equal to +1. And again, just for the end behavior, you have up to the left and down to the right. And I'm going to graph this according to scale, but you got your end behavior. Okay, you got up to the left, down to the right. And the graph is going to cross the x-axis at x equal to 1. So I'm just kind of use this reference to have crossing at x equal to 1, but at -1, the graph is going to touch. Okay, and so just filling in for the in-between sections of this graph. So if I read from left to right, okay, so you have above the x-axis and then getting to the x-axis, and here at x equals -1, the graph is going to touch. So it's just going to essentially bounce off the x-axis, and it's going to rise and pass through the y-intercept at 0, 1, and it's going to descend. And once the graph gets back on the x-axis at x equals 1, it is for the intermediate activity thereafter that you're going to have the motion to be down and continuously to the right. So this will be the general appearance of what we have for the graph of this particular function f of x. So you got your end behavior, You got your zeros on the x-axis where it touches and crosses, and of course you have to throw in, okay, you got the y-intercept at 0, 1. All right, and now for what we have in the case of item number 7, and this is kind of a multiple part here, and we're looking at like the relative minimum and maximum, and also looking at where we have increases and decreases of the graph of the function. And okay, so you have this pattern, okay, throughout. Okay, we're not given specifically just what the function is going to be, but just looking at some of the identifying characteristics from this graph. Okay, and okay, so we have in part A, okay, we're looking at where the function is increasing, and it's increasing over which of the intervals. And what we'll do here is just kind of indicate where you have an increase. Okay, now for the first part, you have downward motion, so the function is decreasing. And once you get to, say, like x at -7, once you get past that, you're going to have an increase, say, between -7 and -5. And then have followed by a decrease, and then we have resuming it with an increase. Okay, so you have this bit of activity, and then we have one more phase of increasing. All right, and so over the intervals, so you have between -7 and -5. And then we have, looks like, between -2 and +3 for this part. And then for the last stretch, okay, we're looking at between 6 and 8. Okay, so in terms of which of the intervals, okay, so you have between -7 and -5. And also between 2 and 3. And also you have between 6 and 8. Okay, so those would be the only 3 interval locations, okay, that signify that the function is increasing. All right. In the case of where we have local minimum, and it says that the function f has local minimum at which x values. Okay, and again, each relative minimum is going to be a dip in the function, and just identifying what we have here. Okay, so you got your dips or minimum. So you have location here. Also have this bottom point. You have one more. Okay, so where we have the x values. Okay, so you have a minimum at x equal to -7. And the next, okay, we have at x equal to -2. And then we have, it's like x equal to 6. Yeah. Okay. And so in terms of which x values, okay, so we've got -7, -2, and also 6. So this is where the minimum or the bottoming out points will occur. All right. Now, in terms of what we have in the next item, okay, we have what is the sign of the leading coefficient of the function. And the way you can go about this is look at the end behavior. And for the end behavior, you have up to the left, or rises to the left. And then you have at the right, okay, you have moving down to the right or falling to the right. Okay. All right, now again, so you have up one way, down the other, and automatically you're going to have that n is going to be an odd value. Okay, And the reason I know this is that if we had n to be an even value, you had moving up both ways or moving down at both ends. Okay, so you have the n is odd, and in terms of the coefficients, okay, with up to the left and down to the right, okay, you're going to have that a of n is going to be a negative value. So for what we're going to have here, okay, so what is assigned the leading coefficients of f, and that is going to be negative. All right, and in terms of the possible degrees of the function, and this is going to go back to what we have in the case of turning points. Okay, and for turning points, okay, you're going to be combining or counting up the total number of relative minimum and maximum. Okay, so in terms of the bottom and relative peak points, you got first, second, third, you got fourth, fifth, and you have 6th point, which is going to be the remaining relative maximum. Okay, so in this case we have 6 turning points. And the thing about n, remember n is odd. And remember, for the number of turning points, now the degree is always going to be greater than the number of turning points. And just carrying this over, okay, to what we have in this particular part, okay, where we have odd values greater than 6. Okay, so definitely 4, 6, and 8 are out of the picture since they're even values. 5 is not greater than 6. So the only numbers that are both odd and greater than 6 we have in the set, we had to be 7 and 9. So those values, okay, will be possible values for the degree of the function on the basis of the number of turning points and the characteristics that define what we have for the graph of a function. All right, now in looking at what we have in the multi-part portions here, and we have for the 2 rational functions that we have in the case of f of x and h of x, and these parts, okay. Okay, so if we're looking at trying to identify, okay, what it's going to refer to f of x as well as what it's going to refer to h of x. Okay, now first of all we have f of x. If you notice in the graphs you have a set of vertical and horizontal asymptotes, and you have like separate sections regarding the graphs, okay, and how they appear, and in terms of identifying which one is going to apply to f of x. First of all, we can identify the asymptotes of f of x. So right now we have f of x is equal to 3x plus 6. And we have over x squared plus 2x minus 8. And what I'm going to do here, I'm just going to go ahead and take what I have and display in factored form. So 3 times the quantity of x plus 2, and for x squared plus 2x minus 8, we have x plus 4, and x minus 2. Okay, and now we had looked at these types of problems, okay, first of all through the vantage point of identifying the domain, and the domain would be exclusive of the zeros of x plus 4 and x minus 2, since we cannot have a zero value denominator. And if you notice, both of these factors, okay, are not in the numerator. Okay, so the factor form is already simplified. Okay, so you're going to have x plus 4 and x minus 2 remain, since f of x is already in simplest form. And since you don't have any cancellation of denominator factors, you're not going to have a hole in the graph of this particular function. So that means that both of these factors will have their zeros to convert to vertical asymptotes. And so we have for the vertical asymptotes, with x plus 4, we have the x is equal to -4, and from setting x minus 2 to 0, okay, we have the x is equal to 2. So we have just in the first round. So looking at the graphs with these vertical asymptotes, okay, so you got for graph A, they don't have -4 or 2. So graph A is disqualified. Right now we got graph B got x equal to -4, x equal to 2. So B survives the first round and got -4, also 2. C survives the first round. Graph D got -4, +2 for the vertical asymptotes. And for graph E, we don't have that match, so we've got -1 and 3. So that goes out. And the same thing for graph F. We don't have that particular match. Okay. All right, so you have two vertical asymptotes. Now, in the case of if you're looking at any other asymptotes, this comes down to the degree comparison. Okay, and so for what we have here, so we have in the numerator, we got 3x plus 6, and with 3x as a higher order term, we have the n is equal to 1, and in the denominator, x squared is the highest order term, so we have the m is equal to 2, and for the comparison of the degrees, we will have the n is less than m, and this is going to signify that we're going to have a horizontal asymptote at y is equal to 0, and so y equals 0, okay, that is going to be the x-axis, and you notice we have with B, C, and D, they all have the same horizontal asymptote. Okay. And now, so we got the asymptotes laid out, and now in terms of any tiebreaker, okay, we got the asymptotes. Well, the tiebreaker, I believe, is going to be the determination of the y-intercept. Now for the y-intercept of this rational function, so we had that y is equal to f plus 0. And what's going to happen here, I'll just carry this on out. Okay, so you got for the numerator, we have 6, and in the denominator, we have -8. So the y-intercept is going to be -3/4. And if you were to express as an ordered pair, you'll be looking at 0, -3/4 on the y-axis. Okay, so we're looking at a value in y that is negative. And if you notice in the case of graph B, okay, you have a positive y-intercept, and I'm looking for a negative, so B is disqualified. And for C, okay, your y-intercept is like 1 point something, so that is going to be disqualified. And for what we have left over for the y-intercept on the y-axis, you have that section, okay, right at -3/4. So you have just above y is equal to -1, and D is going to be the one that satisfies. Okay, so for the graph of f of x, okay, that is going to be graph D. All right, and for what we have in terms of the other rational function, and we have with h of x, so you have 8 over x squared minus 2x minus 3. Okay, now this ratio is already in simplified form, and I'm just going to go ahead and get to the factorization of the denominator. Okay, so for x squared minus 2x minus 3, okay, we'll have x plus 1 is one factor, x minus 3 is the other, and again the ratio is already in simplest form. Okay, so you have these factors remain. So the zeros from the denominator, okay, they will form the vertical asymptotes. So from x plus 1, we have that x is equal to -1, and from x minus 3, we'll have that x is equal to 3. Now I'll go ahead and get to the other asymptote. Go ahead and take care of this one. And for the degree comparison, okay, so I have just the number 8, so n is equal to 0. And again, the reason for that is that we do not have an x term. And for what we have in the denominator, so we have that m is equal to 2. And we have that n is less than m. And we have a bit of history to repeat for whenever n is less than m, you have your horizontal asymptote at y is equal to 0. Okay, so you got your vertical asymptotes at -1 and 3 for x, and again the horizontal asymptote we have at y is equal to 0. So looking at how things size up, okay, so you got for -1 and 3, and the horizontal asymptote at y is equal to 0. Those check out. In the case of graph B, we don't have the vertical asymptotes this time around. Same thing for C. You don't have the vertical asymptotes, and we don't have it for D either. And for graphs E and F, we got -1 and 3 and y is equal to 0. And F, we have also -1 and 3 and y is equal to 0. So we now have A, E, and F in the running. And I believe that the tiebreaker is going to come down to which of the graphs will have the matching y-intercept. So for the y-intercept of h of x, okay, so we have that y is equal to h of 0. And we have 8 in the numerator, and we have 0 squared minus 2 times 0 minus 3. That is going to be -3. So we're going to have that y is equal to -8/3. And in ordered pair terms, we'll have 0 and -8/3. Okay, so you're looking at the y-intercept to be a point that is almost at 0, -3. So you're looking at a y-intercept below the x-axis. And for what we have in the case of the first graph, okay, so it's like you got that one -1, -2, almost -3. So far that looks good. Graph E, well, you got a positive y-intercept, so that goes out. And for graph F, on the y-axis, the intercept is above the x-axis. And so it's going to turn out that for h of x, only A is going to qualify. Okay, so you got D for F and A for the graph of h of x. And we have, now, in the case of 14, now we have another set of rational functions, and these will have a little different dynamic to them. And for f of x, now we have for this particular rational function, okay, so you got f of x, okay, so you have 2x squared plus 2, and we have all over x squared minus 2x minus 3. And if I go ahead and just put this in factored form, now the numerator has a greatest common factor with 2. We got 2 times the quantity of x squared plus 1. And for x squared minus 2x minus 3, then we've got that bit of history to repeat. Same denominator as what we had before in number 13. In the case of h of x, we got x plus 1 and x minus 3. Notice we do not have any common factors between the numerator and denominator that will cancel. So in this case, we have these factors remain. And so for the vertical asymptotes, again, we'll have x equal to -1. And from x minus 3, again, we have that x is equal to 3. And just looking at the other asymptote, if we have one, so we've got 2x squared plus 2, again, over x squared minus 2x minus 3. And in comparing the degrees, okay, so you have the higher order term in the numerator to be second degree, and again we have from x squared, the highest degree term in the denominator. Okay, this leads to m is equal to 2. And so n is at 2, m is at 2, and we have that n is equal to m. And whenever the degrees are the same, okay, we're going to have a horizontal asymptote, but it's not going to be on the x-axis. This time we're going to have that y is equal to the constant that results from taking the ratio of the highest degree terms from the numerator and denominator. So we're looking at 2x squared over x squared, and that's going to go to 2. So you have a horizontal asymptote at y is equal to 2. Okay, so looking for the graphs that have these vertical asymptotes and the horizontal asymptote at y is equal to 2. All right, so we have with -1 and 3, and the horizontal asymptote at 2. Okay, so we got -1, +3, horizontal asymptote at 2. So that part is good. In the case of graph B, we got the horizontal asymptote, but we do not have the vertical asymptotes. So that will go out. C, you got -1 and 3, but if you notice, we have the horizontal asymptote is below the x-axis. Okay, so because the horizontal asymptote shortcoming, okay, C is disqualified. And for graph D, okay, we got the x is equal to 3, but we don't have the x is equal to -1. We got -2 instead. And for graph E, we don't have any perfect match throughout. And for graph F, we got x equal to -1, x equal to 3, and you got the horizontal asymptote at y is equal to 2. So you're looking at where it's going to come down to either A or F. And if you notice, okay, it looks like the y-intercept calculation is going to be the tiebreaker. And in A, the y-intercept is going to be positive, whereas in F, it is going to be negative. So for the y-intercept, okay, so you got y is going to be equal to f of 0. And guess what? So you got 0 plus 2 is 2, 0 minus 3 is -3. So this will come down to -2/3. Whereas an ordered pair, you have 0, -2/3. So just relaying this back. Okay, so you're not going to have 0, -2/3 here. And for graph F, okay, we have for the middle section, you have on the y-axis, and you have a negative y value on the axis. And it looks like that for the graph of f of x, we have f is going to be that which comes the closest to perfectly describing what we have for this first rational function. All right, and in the case of what we have for g of x, okay, this time we have g of x, we have 2x minus 2 all over x squared minus x minus 6. And just looking at identifying the asymptotes. Okay, on the side of whether we have vertical asymptotes, I'll go ahead and factor what I have here. For x squared minus x minus 6, so it's like we'll have x plus 2, and x minus 3. Notice we have no common variable factor between the numerator and denominator. Okay, so again, the x plus 2 and the x minus 3, okay, those are going to remain. So we're going to have for the vertical asymptotes, okay, so from x plus 2 equal to 0, we have the x is equal to negative 2, and from x minus 3 equal to 0, okay, we have the x is equal to 3. Again, just going back to the degree comparison. See if we have any other kind of asymptote. Okay, and so from the numerator, okay, the degree is 1. From the denominator, okay, we have the highest order term at x squared where the degree is equal to 2. So we'll have the n is less than m. Okay, so whenever the degree of the numerator is less than that of the denominator, okay, there'll be a horizontal asymptote, y is equal to 0. Okay. And so we have with the asymptotes, you've got negative 2 and 3. Horizontal asymptote is going to be the x-axis. Okay, so just kind of going through the process. So you got 3, but you don't have negative 2 for graph A. We got negative 2 and 3 for x. And again, we had with the horizontal asymptote for the graph of g of x, that was, again, y is equal to 0. So in this particular part, we got the vertical asymptotes, but we got the wrong horizontal asymptote. Same thing here for C, we don't have the right combination of asymptotes. We got negative 2 and 3, we got y is equal to 0, so that part is satisfied, and we have negative 2 and 3, y is equal to 0, that part is satisfied. And for what we have for graph F, we don't have a perfect match throughout. So this will come down to graphs D and E. Okay, both graphs D and E had the same vertical and horizontal asymptotes. It looks like the tiebreaker is going to come down to identifying the y-intercept. So for the y-intercept, we'll have that y is equal to g of 0. And with x at 0, so you got 0 minus 2 is negative 2. And got 0 minus 6, so that'll be negative 6. And this will come down or reduce to a positive 1/3. So you have for the y-intercept, you have just above the x-axis with the ordered pair 0, 1/3. Okay, so for that one between graphs D and E, okay, so for that which is just barely above the x-axis, looks like we have 0, 1/3 here. for graph E, if you notice, you have just below the x-axis. So now E is going to be disqualified, and it turns out that only D will remain. And so D is going to be that graph which will define what we have in the characteristics for g of x. And now for what we have just in the holdover from the set of inequality problems. And we have for question 19, okay, we got a comparison inequality whereupon we have x plus 8 over x minus 1 is greater than or equal to -2, and it says to respond as an interval or union of intervals. Okay, so for what we have in number 19, okay, so you have x plus 8 over x minus 1 is greater than or equal to -2. And if I reset this and express as a comparison to 0 inequality, so if I just shift the 2 over by adding, okay, so I have x plus 8 over x minus 1 followed by the addition of 2 is greater than or equal to 0. And if I look at combining these terms as a consolidated ratio, and just write 2 is 2 over 1, and your common denominator is going to be, least common denominator is going to be a x minus 1. So I'll just keep the first ratio as it is for now, while I'm adjusting what I have for 2 as a fraction with x minus 1 as the denominator. So it's going to multiply 2 by 1 in the form of x minus 1 divided by itself. So we still have x plus 8 over x minus 1. We have addition, and then we have 2 distributed over x minus 1. So we have 2x minus 2. And this is also over x minus 1. So you have the same denominator, and I can just combine the numerators as they are. And you can just go ahead and get to the final sum in the numerator. Okay, so you have x plus 2x is going to be 3x, and 8 minus 2 is going to be 6. So we have for the consolidated term, okay, this will be 3x plus 6 over x minus 1. And so you have greater than or equal to 0, and this will be referencing what we have also for r of x is greater than or equal to 0. And just now taking what we have here, okay, so we have for r of x, okay, so you have r of x, you have equal to 3x plus 6 all over x minus 1. And for the zeros of r of x, okay, and since the inequality has the equal sign, we'll have to separate what's in the domain apart from that which is not. Okay, so we got for, say, for 3x plus 6, okay, if that is 0, you can have a 0 numerator as long as you do not have a 0 denominator. So if 3x plus 6 is 0, 3x is equal to -6, and with division by 3, x would be at -2. So we'll have -2, and that part is in the domain. However, for x minus 1, the denominator, if I set this equal to 0, I'm going to have the x is equal to 1. And if x is equal to 1, I'm going to have a 0 denominator, and in this case, the rational function will be undefined. So with 1, in a sense, being the other 0, it's going to be that which is not in the domain. And just situating what we have here, we can establish, again, a table of intervals. Okay, and we have revolved about these particular zeros. Okay, so between -2 and 1, okay, -2 is the smaller 0, so we have from the start, we'll have those values of x that will be less than -2, and then going past -2, or bypassing -2, you have those values of x such that -2 is less than x is less than 1, and then for the remainder, you have those values of x which will be greater than 1. And so for what we have looking at testing out, or in this case, sampling. Okay. So for the inputs, okay, so if I supply test values throughout, okay, so like for anything less than -2, I can go with -3. And between -2 and 1, I can go with either -1 or 0 if I choose integers. And then anything greater than 1, I'll just go with the number 2. And we have, again, for the function r of x, okay, so I have 3x plus 6 all over x minus 1 and just creating partitions here, and we have for the case of inputting -3 for x, so we got with r of -3. Okay. What's going to happen here? So you got 3 times -3 is -9. -9 plus 6 is -3. And we got -3 over -3 minus 1. So then we have -3 over -4. And a negative over a negative is a positive. So this will come out to a positive 3/4. And for the case of what we have for r of 0, okay, so we have 6 over -1, so r of 0 will be at -6. And for r of 2, so we got 3 times 2 is 6 plus 6 is 12, 2 minus 1 is 1, so you have a 12-to-1 ratio. So r of 2 is equal to positive 12. And then we have for the sign of r of x. Okay, so for those values x less than -2, we have a positive output. So we're going to have the r of x is greater than 0. Not less than 0, but greater than 0. And then for negatives, R of x is less than 0, so you have a negative output in the second interval section, and for the last you have a positive. And so we're going to have the R of x is greater than 0, and then just getting closer to what we have for the final results here. Okay, so this is the inequality we started out with. And see how we can use the table to determine what the solution to that statement is going to be. All right, so now we have our introductory inequality or original inequality. Again, just rewriting as comparison to 0 items. Again, we have R of x. Okay, so we have 3x plus 6 over x minus 1. Now we're looking at where R of x is greater than or equal to 0. Okay, and so from assembling together, okay, so you have where R of x is greater than or equal to 0. And we have for the solution set. Okay, so you have this in the same direction as R of x is greater than 0. So we're looking at involving the limit values of negative infinity and negative 2, as well as 1 and infinity. Okay, so we're going to have a union of intervals. And for the enclosures, now infinities are boundless, so they will remain in parentheses. And now for negative 2, okay, that is in the domain, and with the inequality consisting of an equal sign, the negative 2 creates the equal to 0 part, so that is going to be bracketed, whereas 1 is not in the domain, and so that will stay in the parentheses, and that will be the solution to that particular last problem.